Come on. Oh, 10:58. It's a little weird. Hey, how you doing? Can you hear me? Yeah, I think you're muted.
Oh, sorry. Hello?
Yeah.
Can you?
Yeah, I can hear you now. Okay, how you doing?
Good. How are you?
Pretty good. Sorry, you said you passed your test. How was that, by the way?
Um, I think I passed. There was
Or
a
like it was easy. You said it was easy, right? It wasn't that bad.
right.
I didn't know if you passed.
Right. It wasn't as bad as I thought it was gonna be. But I got the young modulus problem wrong, and this
Oh, okay.
yeah, and this buoyancy like true or false question wrong.
Oh, okay.
But other
The
than that, I got
qualitative one,
it
yeah.
right.
Okay.
Yep.
How was what was the Young's modulus question? How was that similar, or why was it was it difficult?
I mean, I kind of just like plugged in all of the values that were given, and then it said
Okay.
to find one thing, and then I did that, but I still got it wrong. So I don't know. I don't know why.
Okay. Do you know why you got it wrong though? Or
I don't. I don't know why I got it wrong.
does your professor give you like solutions? Because it might show up in the final.
Yeah. I think she said she was gonna post solutions, but I don't think she has yet.
Okay, that's
Yeah.
fine.
But we can go
Yeah.
over it whenever she posts them.
Okay, let's look at that later. So I took a look at the homework set. It was really weird because I thought it seemed like it was long. It was deceiving because it was like 5 things.
Yeah.
But then when I finally got time to do it, it's like, oh, okay, these are like pretty simple. It's just plugging in, plug and chug.
Yeah.
Like for most of these, how did you? This is due tomorrow, right?
Yeah.
Okay.
I started it because I really only because you put the solutions. That's the only way I to do it. Like I can't. I don't know. I don't get this stuff at all. Like I
Okay.
can't
Well,
read it and just be like, oh yeah, I know what this is. Duh. Like I don't know
yeah.
how the fuck
We're
people.
trying to. I would like to get you to that point where it's kind of like like with every problem. I mean, this like physics is usually just that in general, like knowing what the we talked about last time, like knowing what the like for now. I think what I used last time was Mathematica. I felt like it would take me too long just to create that every time. But then I don't know, which one do you prefer? Feedback would be good. And then this time I'm using like my iPad for my OneNote, which is
Oh.
easier. It's easier because then it's the same way as I would write it on paper.
Yeah, we could just do it this way if it's easier for you. I don't really
Yeah.
mind.
Okay. Yeah, because then like at least like the way you guys would because like the what I was trying to emulate was this sense, in my Mathematica. But I felt like a lot of the assumptions are just like it's because like you were asking me, oh, how did you get this to that point, the equation. It'll be easier to show on paper.
Yeah, right. I agree.
Okay. So
Okay.
which one did you want to cover first?
So on number one, I was wondering why you changed the value of um, R, the capital R.
Oh, that one?
Yeah,
Okay.
you changed it from 8.3 to 0.08 to 62.
Oh, these ones. Okay. So like if you take a look at this, it just that this is just gas constant, right?
It's what, I'm sorry?
Gas constant, the R.
Right. I know it to be as the first value, the 8.3.
This guy.
Yeah.
Yeah. This is the SI version of it. We're talking about like these units.
Uh-huh.
But then like if you're talking about these other units, the bottom doesn't change. Like this is always the case in all like the versions of it. There's always different versions of these guys. And
Okay.
then but then it just depends on like what your units are. It will change your value. Like because it's just a conversion. You haven't seen these other values before?
No.
Okay. Like when you're working with, for example, so I guess we're focusing on one, but you know how like the question is asking you, first of all, I'll tell you my opinion about it. There's like many, like these right here,
Uh-huh.
like it's like making your life like harder because I guess your professor just wants you guys to like go through the process.
Yeah.
Because then you know you're pretty much telling like, okay, don't convert anything and just go with it, and then don't convert this, you know.
Huh.
And then so what I end up doing, because like I've seen this problem before, and a lot of people just like, you know, it's like applying the ideal gas law, because you're given a bunch of these things and you're just solving for the volume of the balloon.
Yeah.
But then like they want you to do, like she wants you to do all this kind of stuff, and it may make sense. And then it's more like qualitative, like, oh, what would happen, you know. uh, the thing is like, so you know it says here like the volume, change the volume to SI units.
Mm-hmm.
And then some of that's what I'm referring to, like when you're going to like solve for it and it's in SI, your units has to be consistent as these guys, and you're going to be using, depending on what your units are, your R is going to change.
Yeah.
Yeah,
So
that's like that's mainly what it is for for R. It all just depends on your unit.
okay. So why did we use the 62.3 in the equation when it doesn't ask for that until the second part? Because it says don't
Oh
use
yeah,
SI until B, until the B
yeah.
portion, right?
I kind of just like, I wanted to talk to you about these. Like I really, you could I want you to just pretty much do, you know, all these ones. I just didn't want to like show something where I would not typically like do what these questions are doing. Like I
Mhm.
would, for my solution, all I wanted to do was just show like the procedure. I think this is like a, like explain why you're doing this, and then like this, it wasn't really, I don't think it was asking to solve the problem. All I did was show like, okay, this is how you would apply it. But for the actual solution though, just
Mhm.
go with what it's asking you. I didn't provide that though.
Oh, okay.
Yeah, it
So what
wasn't.
you did was just solving it, but using the not SI.
Yeah, but does it make sense to like when it's saying like, I guess looking at these questions, do you know what it's asking?
Mm,
Like for
I
example,
I
like
think it's
B.
asking what is the difference in the numbers when you don't convert.
Yep, that's what I'm getting from these. Like your professor wants you to like not convert that parameter and then compare it. What will your answer be? You know, how is it different?
But why does that matter?
That would be a question to her. Like it's like I said, that's why I skipped it. I was like, why are you asking these things? But
Why are you telling me to do it wrong and compare it
yeah,
right?
yep.
That's
It's a little confusing, and I don't know why you would do that. But in a sense, just like follow what she's asking.
okay. You start solving the problem with the current numbers without converting the units of volume to
Yeah, you have mismatched units. Like that's not good. But you know, whatever.
okay. So what's mismatched about it?
Like so, you know, when you're saying you start solving the problem using the current numbers, right?
Mm-hmm.
And then without converting the units of so this
Oh,
one,
like keeping the Celsius.
yeah,
Is that what she means?
yeah. So like for this first part, like, let's look at it. You start solving the problem using the current numbers. So these numbers gives you the torr, and then Celsius, and then liters, right? Yeah. And then what was this? Using the current without converting the units of volume to SI. So what I think she meant, this volume is probably like this last part, right?
Mm-hmm.
Yeah. So when you solve this guy, just use the units. Don't convert it to
Mm-hmm.
like what I did here, you know?
Right,
Like,
right.
and then this next one right here, you do all the changes except for the pressure. So here. you do all the unit changes except for the pressure. So I guess you can change, like you keep the torque, but you're changing these guys, right? Like the volume.
I thought we were keeping the volume, which is the right way, which is liters, no?
Yeah, that's the
Why
right
would
way. But then
we why would we change the volume?
like you do all the unit change except for the pressure, it says here.
Right, right. But what would you change the liters to? What would you change the volume to?
Oh, I see what you're saying. Let's look at the R. Yeah, like I said, this is like one of those. So
Because I know to do it the right way, you had to change Celsius to Kelvin,
yep, yeah.
but then you can just keep the rest, no?
The pressure. Let's look at, because she wants you to pretty much keep the pressure, right? As torr, yeah, except for pressure.
So what's the right unit of pressure then?
It would be the SI. It would be like ATM, I believe.
Oh, okay.
Yeah, it's usually ATM, not
Oh,
Pascal. There's no Pascal over here. Or wait, ATM is this guy. This joules is, yeah. It would be you change it to Pascal is the SI. Yeah, change it to Pascal. ATM would be liters.
I thought ATM was pressure.
Yeah, but
Atmospheric pressure.
no, like ATM is just a unit of pressure. It's just a
Oh,
unit of pressure, yeah. But like if you could also use Pascal. Pascal is like another pressure unit,
right.
which is like from these joules. You could get that because joules.
Okay. All right. And then just whatever it's telling me to change, I change it and then just do the process that you did on the
Yeah, and then
Okay.
like explain the difference. Yeah, let's do that.
Okay. All right, yeah.
It seems pretty easy, but yeah, like that was the one that I was like thinking like nah, I'm not gonna go with that. What about number two?
Yeah. So I was barely looking at number 2 right before I got on the phone,
Okay, what do you think
but
of
I
it?
didn't finish. I didn't finish looking at it.
Okay, let's like look at it.
That's 2. Okay.
Yeah, so if you read this, so like you said, you're taking like a lot of these is very it's like review in essence. If you're taking like chemistry,
Mm-hmm.
uh, it's like applying just, and then yeah, thanks for sending me that chapter 18, and
Mm-hmm.
I took a look at that. Yeah, most of it is review. Like Boyle's law, Avogadro, right? Charles.
Yeah, right.
Yeah.
Yeah, I remember Avogadro's from chemistry, but the rest, kind of fuzzy.
Yeah. So like a lot of it is knowing, just stepping back, is when you're solving these problems that are chemistry related in terms of like we didn't really get to a lot. I know associated with it is also like gas stoichiometry and then partial pressures. There's no problem that's like related to that. All of this is like ideal gas law problems pretty much, and then I think linear expansion, yeah. But when you're solving for that, it's just applying that equation. Like you read this and you look for things, and then this right here is it's a sealed container. As it says, sealed container, right?
Mm-hmm.
So the equation is going to change, and it gives you like, so you wanna look at keywords. So it gives you like this guy and that guy and that guy, right? So this number is like not right. This is supposed to be, I don't think that's like too high or like too low. It'll be 10 to the negative 10 to the fifth, which I put
Right,
in
right,
here.
right.
Yeah.
Right. Yeah, yeah. Okay, yeah, cool.
Yeah, I've seen
Yeah,
this
I'm
like
pretty sure that's what that was.
example before. I was gonna ask you about that, but I was like, oh, okay, that seems like it doesn't make sense.
Yeah.
So this is how you would do it. So like the main equation, I guess, what I would think is applied to a sealed container is this guy. This is the one that you would apply, and like, because a lot of the assumptions, if you remember ideal gas law, like if you you usually solve for the number of moles
Mm-hmm.
for one case, and then that number of moles you apply given like the new pressure, new volume. Same with the number one.
Yeah.
So, and then you're given everything but like one parameter, right? Something like that.
Right.
That's like the system of like how it can be applied.
Okay.
And then for this one, it just changes your equation because it's sealed. So this is the equation for it.
So what's the original equation of that?
Okay, so when you're talking
One V1
about,
equals P2 V2?
yeah, it's this guy.
Okay.
And then if you look at your the lecture notes, it talks about this. I think it's on sealed container. But then your temperature isn't given to you. Because like then it becomes a constant, yeah? Like if it involves a sealed container, I think it's on page 1813.
Okay.
This is like one of those things like, oh man, like I know this, but I totally forgot it. It's just like one of those terms. But this is what you do if you have like a sealed container. You instead of using like PV equals nRT, that equation, the PV becomes constant, and you can just make this equal each other. And then like another thing with this problem is since it's sealed, the volume is additive. So, you know, like I think it tells you like that if the vacuum chamber has a volume of 2 liter, so the first time it's 1, and then it's connected to the vacuum chamber. So you just add that to get V2.
Mm-hmm.
It's not V2. It's the change. You have to add it to the original because it's sealed.
Okay.
And then the one thing to know about sealed is your number of molecules, your moles, doesn't change.
Right. It's a constant.
That's why it's not in this equation.
Okay. I have a question. How do you know when to use the ideal gas law, which is PV equals nRT?
Yeah.
Or if you're going to use PV equals NKT?
NK, you know that equation, it's like a weird one. It's like Boltzmann constant, NKT, you said, yeah. It's
yeah, NKT.
That K is a Boltzmann constant. I would say that the way I've seen this a lot is like PV with the small n RT, gas constant temperature. And then when you're given this like KB in, you know, like I don't know if there's a problem in here. I don't usually see that second equation. It's more of like the nRT. It's probably going to be not given to you. It's a weird one, yeah, because it's probably not going to be given to you because then it's already a constant. Let me see if there's actually like a, and I looked through the examples. It doesn't really have one that refers back to that.
I mean, maybe we haven't gone over it, but she just mentioned it.
For the most part though, like I haven't seen it like as much as like PV equals small n RT. So use that one.
Okay.
Like the other equation is definitely, it's like a special case.
Mm-hmm.
Okay.
Okay.
So
Cool.
does this one make kind of sense now?
Yeah.
Okay, cool.
I mean, we're using the P1 V1 equals P2 V2 because there's no temperature involved, right?
Yeah, no temperature. The main equation for that is PV initial over T initial equals PV over T final. But you're not given like the temperature. So I would just apply PV times equal, you know, initial and final. It's one of those things like what's given to you when in this ideal gas law, what's given to you, and then what can you assume? Yeah. And then if like for sealed, just use this. Like you're gonna get many different like problems, and this is one of them. Sealed type problems.
Yeah.
Okay.
I think they're all going to be sealed because she said all ideal gas problems involve gas in a sealed container.
I would like say like because then that equation can't be used then differently. It can't be used differently. Like it only if it's a sealed glass container. Did she say that? That's because then you have to say it. It's sealed.
I mean, that's just a remark she said. All ideal gas law problems involve gas in a sealed container.
But then you know the equation itself. I've seen like the equation not used this way, like the one that we just did, right?
The
This isn't sealed. This one isn't sealed. It's outside.
right, yeah, that's true. Yeah, that kind of confused me too. I was like, wait, but it's out in the open, so
I mean, you can say it's sealed by what? The atmosphere. I mean, like, you know, before you go to, but as I know it, it's not always the case. It's not always sealed.
okay.
But the using the ideal gas law, you can assume the fluid air can, like air itself, it most of the time it's like,
Okay.
and that's the only time you can use it, or else you have to use something else. You can't use that equation.
Okay.
All right. What about this guy? Number 3.
Certain metal has a coefficient of linear expansion. Coefficient of linear expansion. What's
Yeah.
linear expansion?
So that equation itself here, take a look at that. There's two things here that you guys have in chapter 18 that maybe like it's good to like go over, but there's linear expansion and then there's a volume expansion. Have you seen those wordings before?
I mean, I'm assuming displacement.
Yeah, very much so. A lot of it is an expansion, right? But
Mhm.
so like, but then it really goes back to like, do you remember alpha, the term alpha, and then beta?
Yeah, but those terms confuse me. Whenever I see a symbol for a number, I always get confused.
Just breeze through it. Okay. Well, a lot of it is just knowing the physics of the symbol. Like alpha itself, when you're let me just define it. So alpha is the linear expansion, and then beta is like the volume expansion. And then linear expansion is like, you know, it's usually associated with temperature.
Mm-hmm.
It is. It's not usually. It is. And then so if something is heated, it's gonna expand. If something is like you know in a cold environment, it's gonna contract, right? It's gonna be negative expansion or contraction. And if
So wait, hold on.
okay,
Alpha's linear,
yep.
beta's volume.
Yeah, beta's volume. Yep. And then this might be a very good equation. Beta is 3 times alpha. So beta
Oh
equals
yeah,
3
she
times.
went over that. I remember she mentioned that.
Okay, but yeah, so that you're gonna use in the next one, I think. Yeah, every time you do like a volume expansion, you have to use that equation. That's the only way.
Yeah, like alpha is like the change in length in one direction.
Yeah,
Pretty much like
and
the
then
surface area, and then the B is like the change in volume,
okay, so yeah,
right?
that it's not the theory of that isn't that bad. I mean, it's just okay. You have something heated. Volumetric expansion is like all 3 directions expanding.
Uh-huh.
And then linear, obviously, alpha, it's only one unidirectional. It's like one of those directions.
Okay.
And each one of these guys can be looked up in a table. So meaning they don't have to give you that. They don't have, you know, if you ever do see it in like a quiz or test, they could just tell you the material, and then it's a material property, like expansion coefficients, alpha and beta. These are material based.
Right.
Yeah.
Okay.
So for this one, they made it easy for you. Like, you know, they just said a certain material. They don't tell you what metal it is. And it says coefficient of linear expansion is this guy, right? Oh, I'm not marking. It's this guy. And let me see. And then they give you like these guys, right? They always give you temperature.
Mm-hmm.
And then like what is it asking you? And it says, what is the percent change? What is the percent change in density? This kind of tells me, like, you know, when you're seeing percent change, this equation typically is like something times 100, right? It's like you have an initial here and then a change.
Yeah.
That's like, yeah, that's just what it's asking. So this equation is like probably not in like the lecture, but it's like, okay, what is a percent change of a quantity. It could be something else. It doesn't have to be density. It's usually just like initial time, or it's a change over initial times 100. And that's what I applied in here. So, okay. There's also another thing, like, you know how like when you're applying
What's GFA that you wrote?
GFA.
G and then F and then A. The colons?
Oh, these guys.
Yeah.
A lot of people. Okay, so these ones. So this is the way I usually write. You know how like in my Mathematica, I had like givens and find and answer. And this is just shortcut for it.
Oh, okay.
Yeah.
Fine answer. Okay. Okay. Okay.
GFA. Okay. All right. So for alpha, typically when you're applying these guys, you know how like this is always given to you, and for the most part, it's either Celsius or Kelvin, right?
Right.
And then this is just one thing you probably noticed already. Like if you're given like a Celsius, for the most part, you always want to convert it to Kelvin. That's like the automatic thing to do. It's like, oh, let me convert everything to Kelvin. You could do that. You don't have to though. When it's like a ratio, like if it's a ratio like this, temperature changes. You can leave your like this guy. You can leave this guy as Kelvin, and your temperature can be in Celsius. It's just extra work for you to change it to Kelvin. The difference, because you're gonna take the difference of that guy, right? You're taking the difference of that guy, yeah. So
yeah.
the difference of like 2 Kelvin numbers is the same as the difference of 2 Celsius numbers. So so you don't have to like convert this to Kelvin. You can leave it as Celsius and still work, and with the alpha, it won't change your answer.
Okay.
And I think that's what I was trying to do in here.
Okay.
And let's see, and then so now that you have the difference in temperature, you always need that for linear expansion because it's in the equation. The equation right here. And so what you have to do is like find the difference in pressure or in density. So it's change in density, and then this is like the initial density.
Okay.
But you're not given those things. So what you could do is just leave those guys and then just times it by this one, which is like, initially this is like beta, delta T, and this one is 3 alpha. And then you just plug in what you know, and then you're gonna see like this pops out, and then so your densities here, you just apply that equation, change over initial times 100, and it's never negative because it's like a change. And so if you've seen like this, this just means an absolute value. So then you'll get your answer.
How did you isolate the oh, you just divide the initial over to the other side?
Yep, because like that's the equation for like the change in density.
Okay.
You don't know it, so can't really do anything, but it's convenient it's asking that.
Okay, yeah. Okay.
Yeah, so like I said, this one isn't bad.
Oh.
Like they could probably, the way it could vary, they could change this guy. But yeah, so I think a lot of the problems here are like ideal gas law and expansion. And then so this one's linear expansion. And then the next one I think is volume expansion. This guy. Does that make sense for linear expansion?
Yeah.
That I didn't really like that question. I think there's because like it's like if you were to like practice that wouldn't be a good problem, because then it's asking you about something you don't know, which is like the density. I think there's a problem in the lecture, the expanding pipe one, which is good because it's just okay, change in. It's pretty much it's kind of similar. This one is a change in the length. Yeah, right. I think it's a change in the length. Expand, yeah, delta L over L. but it gives it to you in like length of pipe. And then you're actually getting like a number instead of like a percentage. But this one is in density. Okay.
Hold on. A novice cook. Fish, deep frying some potatoes, spills lots of cream and heats the oil.
Okay, for this one, I guess tell me what you think you're gonna do.
Coefficient, linear expansion. Coefficient of volume expansion of olive oil. To his consternation, olive oil spills. So much.
Oh yeah, this guy too. The question's a little weird.
Yeah.
It's like to his concept. Okay, some olive oil spills over the top. So spills over the top. How much spilled over the top? I guess in terms of like oil and then how much spilling. That sounds like a volume, right?
Yeah.
Let's look at it. Yeah, it is a volume. So it's a change in volume because it's like not the full volume. What's the volume now? How much spilled?
Yeah.
How much spilled is the change in volume? Like a lot of this is like don't get the word, like don't get bogged down, hang up in the wording. But it's like much practice is always for these problems. It's just like what are you looking for? What keywords, right? And then what is it
Yeah,
asking you?
like change in volume is what you're looking for.
Yeah. And then like they could word that in so many different ways, which sucks. Like it's always, I mean, in essence, all of it is just comprehending like all the givens, knowing what's being asked, and then a solution.
Mm-hmm.
Okay. So this one, right? This one is what is this parameter?
The volume?
Okay, yeah, the volume expansion. What about this guy?
I don't know. Linear something.
Okay, oh, linear. Okay, this one's a volume. Good. But yeah, so these are new concepts. You already know these two. And then most of the time, I mean, for what the easy problems will give it to you. Like the ones I've seen, maybe on an exam, they won't give you directly what these are. Like maybe you have to look it up from a table. But that shouldn't be like maybe you can just. I think the table that I'm referring to is in the lecture. Given the material, you can definitely just find these guys. So.
Oh, okay.
All right. So since it's asking you, what is it again? Like it's asking you the change in volume.
Mm-hmm.
I mean, taking a look at this, it's like I would just create that equation, change in volume. So wait, if you go back to that guy, so it says oil and aluminum. It says something about oil and aluminum. So spills over the top. So what you could do would be the difference between the oil and the aluminum, because you're gonna use this guy.
Yeah.
So it will just be this delta V of oil and then delta V of the aluminum. And that equation, right? That equation is just this guy.
So why does the volume change? Because it gets heated?
Yeah, because you have the delta T. You have the delta T.
Oh, okay. Right. Okay.
Yeah, every time you have an expansion problem, there's always some temperature. And then every time you have a temperature change, because you're expanding, volume is going to change.
Okay. I see.
And let's see, let's look at this.
Temperatures?
Yeah. So, oh yeah, the delta t, I kind of just like lumped these guys in there. I didn't want to do like another equation, but this delta t is like the t2
Wait, so
minus t.
how did you know that alpha was the 24 times 10 to the negative 6?
Because it's linear. Does it say linear? I thought it said linear.
Oh, linear expansion. Oh, okay.
Yeah. And then like if you look at the other way, if it doesn't tell you that, is like typically a lot of these alphas, you know, when we're talking about alpha and beta, linear and volume, like the linear and alphas are associated with solid stuff.
Mm,
And then the betas and volumes are associated with liquid stuff. That's just what it is.
okay.
Like, and you know, there's different ways of asking that, but yeah, everything is in here. It says linear, and then it gives you the value, and the material. It gives you the material as well.
Mm-hmm.
But you know, in an exam, they're definitely not going to give you one of them. So let's see.
Okay. That makes more sense now.
Yeah, and then you just apply the equation, same way as you do. You do like beta, delta t, and then there's the volume change, and
Mm-hmm.
you know, and then you simplify it. You could just do this first, and then you do that, and then you know,
Yep.
because you start volume and then change, and then you get this.
Okay.
See, like the hardest part is just figuring out like the math isn't hard. It's figuring out that equation, setting it
Right.
up.
Yeah, setting it up is always hard for me.
But like I feel how's like that's why I want to know like how similar, how different like the equations for the exam versus like the homework. It did change a lot or what for the first exam?
Um, Not really, no.
Like it's a very similar configuration of the problems in a sense.
Yeah.
Or, okay, that's good. That's always a good thing. A
We
lot of
don't have any word problems. That's the thing. There was only 2 word problems. Or
okay.
3, I think. Or 3, yeah.
And then the Bernoulli didn't even show up.
No, Bernoulli wasn't even there, and that's what I was studying for hours.
I know. But I think like you said, like maybe you thought too hard, you know. Like
Yeah,
maybe
I mean, I just assumed that she was just gonna put like the lengthiest equation,
yeah, but
but she
she did
ended up
say,
just using like the easier ones, which I didn't really practice. Like I didn't
and
really
that's what
practice Young's modulus.
sometimes that's like one of those things like you try to omit like the easy ones, and then that's and because of all that info overload on your head of like practicing
Yeah.
the other stuff,
Mm-hmm.
yeah, okay, it's like oh shoot, and it's easy. I think maybe the next one, this one, how do you feel about this one versus like the chapter 14? It's not as bad, right? Because you've seen it
No,
before.
I honestly think it's a little easier. I just have a hard time conceptualizing like what the word problems
Okay, my
like.
best bet is just you have this in Chegg. So if you look at like a lot of the other problems in chapter 18,
Yeah.
I think there's like 1 to 40. Yeah, or I didn't want to do all of them, but if you want to do those, they're kind of very similar. Like, and the more you do it, you tend to like build like, okay, these are usually the ones being asked. You know, like you're gonna see like which one, how the configuration of the questions are, and
Yeah.
then like building that traction and then comfortability, then build knowing setting up the equation wouldn't be as bad.
Yeah.
Okay, so I think yeah, that's like number 4. Did you want to try like the extra credit one?
Not really.
It may appear in the exam. It's not that bad too. It's not that bad. This one's the easy one. It's just something to I mean like it's like a way to apply it, but maybe it's not. It won't be asked in the exam. Is what I'm saying. It's a little too hard to conceptualize.
Yeah, no.
I'll just explain it though, since
Yeah,
I had.
just go over it if you want. Yeah.
Okay, cool. So what this is doing is like really just telling you, like, so you have this slab, right? Slab, and then this guy's a slab, and then there's this expansion and there's this angle, and then
Mm-hmm.
the initial length of the slab from like I guess this point to this point is this guy, and then when it deforms in angular, like it'll deform angularly. You're obviously this is gonna be different, right? this L
Mhm.
prime is going to be different from L.
Right.
Yeah. So what it's telling you is like what it's wanting to know is what is this angle change? This angle change is like, but then what it's giving you is, okay, you have a change in temperature. Okay, that's good. You're gonna need that because you're gonna need that because you have this alpha. Every time you have an alpha, there's always a delta t or two t's.
Mm-hmm.
So then if you didn't know what the solution is yet, like, okay, so you have this L and an L change. How am I gonna get those? You're probably gonna wonder like how you're gonna get it. So I kind of just like added that here. It's like, oh, I know I'm gonna need this, but I don't know how I'm gonna find them.
Uh-huh.
So, but this equation, the the change L is just the L plus the deformation, right? This expansion deformation, whatever. And so you set that up, and I mean, it would be nice to draw a picture in all of these cases. It's easier to see like a free body diagram.
Mm-hmm. Why is there a +1?
Oh, okay. So you know how it's like an original plus, it's the original length plus the deformation, right? This is the deformation
Okay.
because it's expanding. It could be contracting as well, but in this case, it's expanding. And then this is the new length, so it's the original length plus the expansion. And yeah, you simplify that. I just put a 1 there. Anyways, looking at this guy, now you see like you know what you have to apply, right? Like it's a cosine. It's like a cosine issue.
Mm-hmm.
Yeah. So
Uh-huh.
now you have a fighting chance thing. Is like, oh, maybe I can cancel something out.
Yeah.
Since you want this guy, and just work with the equations that you have. So I did, and then like plug in what you have and see if something cancels. So something does cancel. Thank goodness, because then this L prime has L, so it cancels, and then you're left with the ones that you only have. And so that's it. That's how you do that.
Wait, L and K canceled?
Where's K? It's not K. L.
Oh, oh,
Yeah.
okay.
Yeah.
Oh, okay. I see.
Yeah, no, chicken scratch. That's why I like typing. See what I mean?
Yeah. Yeah, true.
Yeah, so that's pretty much like that. If you ever like I said, the more problems you do, like before the exam,
Yeah.
the,
I
the
just
more.
hate doing that. I hate doing these problems so much.
Yeah, I mean, like this class will pass.
Yeah.
Yeah, it's not
It's
that
already
bad.
my third physics class and I still hate it. I haven't gotten used to like anything or enjoyed anything.
Is this class or you guys' final physics or?
Yeah.
Oh, it is. That's
Yeah.
good.
Yeah.
There's more physics, obviously. I can just let you know, but you probably don't care.
I really don't.
Yeah. But like as far as like yeah, like this isn't like the end. I think I looked ahead. The end of this is we're not even going to heat transfer. So but this week's or not? Are you guys doing this for another week or is it just this week?
I think we're gonna do it for another week because there's a part 1 and a part 2 PowerPoint.
Oh my, okay.
Yeah.
I'm hoping the part 2 isn't that bad. Okay.
Yeah.
And what about homework wise?
She just gives a homework once a week, typically, with like
Oh,
this many problems. So I'm sure it won't be too bad.
okay. Yeah, show me or like send me the other homework later on for next week if we need to
Okay.
go over it. Because then your exam is gonna be when?
It's on September 30th.
And that's like what the couple after next week, the following week? I think so.
Yeah. September 30th, I think it falls on a Tuesday? Wednesday.
Okay. Okay.
Next Wednesday.
So you have like this week and next week. I think you'll be fine.
Yeah, I just need to practice them, but I really don't want to.
I know no one wants to, but like why I would say is this time try to like this is a good thing that we're doing this now. Like I like doing this because then at least I can space out the lesson, you know,
Yeah.
and then like explain bits and pieces for each one.
Mm-hmm.
The and then yeah, this like I said, this for this next one maybe just do a couple of these, and then for the next one we'll focus on. There was really nothing that hard that you kind of like prompted me. I was like, okay, there was nothing too bad. I just did the solution. So
Yeah.
what about the lecture? Was there something else there?
Really just um like knowing what equation to use when there's a word problem, and
Okay.
um
For those ones, it won't tell you like this is a Boyle's problem. This is like Avogadro or Charlie. You know, it won't tell you that one.
yeah.
The like as I always say with chemistry, it's just knowing, like especially for PV and NRT ones, know that like they can ask you either any of those, right? They can ask you what pressure, what volume, what temperature, right?
Right, and it's just like manipulating the
They'll never ask you for R. So
right.
like you're given all of them except for one. You always want to solve for like the N. Give it. Oh yeah, this can also get harder by giving you like chemical equation. You know,
Oh, what?
a chemical equation. You've seen those before, right? Chemical equation.
Yeah.
Yeah. When you have that, you're given like the moles. This is like chemistry, like very much chemistry only. And then given the moles, you have to find it gives you molecular weight, all that stuff. And then there's a relationship when you're changing the reactants to the products. That's like gas stoichiometry. I don't know if you guys will cover that one.
I don't know, probably not, because I didn't
Oh,
even do stoichiometry. All I did was chemistry 1 and 2.
yeah, but I thought like gas stoichiometry. I'm pretty sure that's in one.
Is it?
Yeah, and then, do you remember doing like partial fraction, not partial fractions, calculus? I'm thinking about my calculus class. Partial pressures.
No.
Yeah, yeah, it's like one of those things. But if you guys are not doing that, that's good. I mean, PVNRT is like the very basic one. I remember doing that, and then other stuff is what I'm saying. There's like other things.
Yeah, I'm sure it gets very complex, very yeah.
Okay, okay. So
But
I guess
um
that makes sense. Like a lot of things make sense on this
mhm.
chapter.
Yeah, it
Um,
wasn't too bad.
and then like, do you? I know for this week we didn't really do an appointment because this was a makeup for last week, which we didn't do.
Right, right.
Yeah.
Um
Let me
for
know if we need to do one for before the exam though.
yeah, for sure we'll do one before the exam, but I'll let you know like later this week what day,
Okay.
hopefully like a day before the exam or like 2 days before the exam.
Okay, 2 days, yeah. Shouldn't be that bad. And then like just shoot me any of the like, you know, confusing questions you still have, and if there's like homework problems, I can do the same exact thing next week.
Okay, that sounds good.
Okay. All right, Allison, thank you.
All right, thank you. Have a good week.
You too. All right.